we're going to talk about is a partition of the closed interval from a to b. That's a strictly increasing sequence of numbers belonging to the interval, starting from the initial point a and arriving at the final point b, denoted by a delta symbol. So if we look at our example down here, the partition of the closed interval from a to b would be this strictly increasing sequence of x values, starting with x sub 0 and ending with x sub 5. This would be your partition of the closed interval from a to b. Now, the distance or space between each of these given x values we call subintervals of the given partition. Now, I want you to note that up until this point, we have been dealing with subintervals that have all had the same exact width when we have been approximating area under the curve. Today, we're going to show you that that's not always necessarily the case. Sometimes you will have certain subintervals that have greater widths than other subintervals in the given partition. Now, the norm is going to be the width of the largest subinterval of partition delta, denoted by the delta symbol with 2 bars on either side. Now, just like we said before, the width of your subintervals are not always going to be uniform. They're not always going to be the exact same. Sometimes you will be given subintervals that have different widths. And when you do, just know that the width of the largest subinterval, in this case, from x sub 3 to x sub 4, that is going to be called your norm, and it's denoted by this symbol right here. Now, a regular partition is what we were talking about earlier when we were approximating area under the curve with rectangles. A regular partition is a partition where every subinterval is equal in length. So if you recall in previous lessons, when we were approximating area under the curve with rectangles, we would have to find the base and height for each of those rectangles. And when we were doing this, the base was actually the same for each of the rectangles. It was delta x, and we found that by using b minus a over n. Now, because the base of each rectangle is the same exact measure, they were all equal to delta x, that means the width of each subinterval in this given partition is the exact same, meaning that our norm could have been the width of any of the given subintervals in this given partition. When this occurs, we call it a regular partition. Now, a general partition would be a partition where the norm and the number of subintervals are related in the following way, where b minus a over the norm has to be less than or equal to n, the number of partition subintervals. So as the norm approaches 0, the number of partition subintervals approaches infinity. And the way we write that with our math symbols would be as the norm approaches 0, n, the number of partition subintervals, would approach infinity. So what this is saying is that as your norm, the width of your largest subinterval within a given partition from a to b, as that approaches 0, meaning the width of your largest subinterval gets closer and closer and closer to 0, it gets smaller and smaller and smaller and smaller, the number of subintervals that it's going to take to span that entire interval, that entire partition, has to approach infinity. Because as the width of your largest subinterval gets smaller and smaller and smaller, the more subintervals you're going to need to fill that given interval, that given partition. So as your norm approaches 0, the number of subintervals would approach infinity. Now, a Riemann sum says let f be defined on the closed interval from a to b, and let delta be a partition of the closed interval from a to b, given by this given inequality, where delta x sub I is the width of the ith subinterval, the closed interval from x sub I minus 1 to x sub I. If c sub I is any point on the ith subinterval, then the sum from I equals 1 to n of f of c sub I times delta x sub I is called a Riemann sum of f for the partition delta. Now, if you recall, we've dealt with sigma notation before when we were approximating area under the curve with rectangles. And this is the exact same thing, where I is going to represent the index, which interval we're on, and c is going to represent your x value, whatever x value you're plugging into your given function. Now, the key here is to note that this times this is actually an area formula for a rectangle, where f of c sub I is going to be the y value of your function at x, meaning it's going to be the height of your given rectangle. Delta x over here is going to be the distance between x values, or the base of each rectangle. So what this is saying is that you're actually going to add together, which is what this sigma means, the area of a bunch of different rectangles. It's going to represent the sum of an indefinite number of rectangles under your given curve. This is how we're going to approximate area under the curve, with the sum of the areas of rectangles. And that is what a Riemann sum is. Now, a definite integral says if f is defined on the closed interval from a to b, and the limit of the Riemann sums over partitions delta is the limit as the norm approaches 0 of the sum from I equals 1 to n of f of c sub I times delta x sub I exists, as described above, then f is said to be integrable on the closed interval from a to b, and the limit is denoted by the limit as the norm approaches 0 of the sum from I equals 1 to n of f of c sub I times delta x sub I is equal to the integral from a to b of f of x dx. Now this limit right here is called the definite integral of f from a to b. So we just said that this Riemann sum right here, starting with this sigma, is a way to approximate area under the curve. It's the sum of the areas of a bunch of different rectangles under the curve. Now, if we take the limit as the norm approaches 0, meaning your subinterval with the largest width approaches 0, meaning that you have an infinite number of subintervals under your given curve from A to B, meaning you have an infinite amount of rectangles from A to B. This is going to give you the exact area under the curve. Now let's think about this for a second. Let's say you have a function, a curve, and you want to approximate the area under the curve on a closed interval from A to B. If you create a certain amount of rectangles, it's going to give you a close approximation of what the area under the curve is. But let's say you add more and more and more rectangles on that given interval. Well, then your approximation is going to get closer and closer and closer to the exact area. And let's say you keep adding until you have an infinite amount of rectangles under the curve on that closed interval from A to B. That is when you're going to have the exact area under the curve. And having an infinite amount of rectangles on that closed interval from A to B is the same as saying the limit as the norm approaches 0. Because the norm is just going to be the width of your largest subinterval. So if that is approaching 0, if that's super, super, super small, that means you're going to need an infinite amount of rectangles to fill that given interval from A to B, thereby giving you the exact area under the curve from A to B. Now, if we look down here, we see something called a definite integral of f from A to B. Now, this is just another way to calculate the exact area under the curve of your given function f from A to B. Both of these things are doing the exact same thing. They're adding together the areas of an infinite amount of rectangles under your function f on the closed interval from A to B, where c and x both represent the x values, delta x or dx both represent the width of each subinterval or the base of each rectangle, and f of c sub I or f of x represents the height of each rectangle or the y value of your given function at each of these x values. Now, within your definite integral, you have this a and b. That would be your lower limit of integration and your upper limit of integration respectively. So that's just telling you what x value to start at and what x value to end at for your given interval. Now, I'm creating a whole new slide just to tell you exactly what I told you before. All of these things mean the exact same thing. They all find you the exact area under the curve on the given interval from A to B. This one right here is telling you to add together the area of an infinite amount of rectangles. You know it's an infinite amount of rectangles or an infinite amount of subintervals because it's a limit as n approaches infinity. And remember, n is the number of subintervals of your given partition. So if you have an infinite amount of rectangles and you add together those areas, that gives you the exact area under the curve. This right here, exact same thing. You are adding together the area of an infinite amount of rectangles. And we know it's an infinite amount of rectangles because your subinterval with the largest width, our norm, approaches 0, meaning that you have an infinite number of subintervals under your given curve from A to B. That means we need to have an infinite amount of rectangles in order to fill that given partition, that given interval. And if we have an infinite amount of rectangles and we add together the area of those, we will get the exact area under the curve. This right here, just another way of saying each of these. We are adding together the areas of an infinite amount of rectangles on the given interval from A to B to get the exact area under the curve on that interval. Now this theorem, the definite integral as the area of a region, says if f is continuous and non-negative on the closed interval from A to B, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is equal to the integral from A to B of f of x dx. So this theorem is just proving to you exactly what we were just saying. The integral from A to B of f of x dx is just giving you the exact area under the curve of your given function f on the interval from x is equal to a to x is equal to b. It's adding together the areas of an infinite amount of rectangles in that given region in order to give you the exact area under the curve on that closed interval. Now let's talk about indefinite versus definite integrals. So the indefinite integral of f of x is a function that represents the antiderivative of f of x, whereas the definite integral of f of x is a number that represents the exact area between the curve of f of x and the x-axis. So note in these two examples, the key difference between an indefinite integral and a definite integral would be your lower and upper limits of integration. Your indefinite integral does not have a lower or a upper limit of integration, meaning that this given integral right here is just going to be equal to the antiderivative of your function plus c. Whereas in a definite integral, you are given a lower and an upper limit of integration, meaning that if you were to evaluate this given integral, you should end up with a number because you are calculating the exact area under the curve of your given function on the interval from a to b. Now, we will learn how to do this in the next few lessons. Now let's take a look at how Riemann sums and definite integrals compare. So this says use the graph and the information provided to determine whether the Riemann sum is greater than, less than, or equal to the definite integral. So part A says the closed interval from 1 to 5 is partitioned into n subintervals of equal width delta x, and x sub I is the left endpoint of the ith subinterval. So right here, we have a Riemann sum and we have a definite integral. Now a Riemann sum adds together the areas of a certain amount of rectangles, n amount of rectangles, in order to approximate the area under the curve from x is equal to 1 to x is equal to 5, the area of this pink region. So this right here is going to be an approximation of this area. This over here, the definite integral from 1 to 5 of our given function, is going to be the exact area under the curve from x is equal to 1 to x is equal to 5. So we have to figure out, is this right here an over or an underestimate? Well, because we are using left endpoints, this right here is going to be a left hand or left Riemann sum. And because our function is decreasing on the given interval, this left hand approximation is going to be an overestimate, meaning that this value right here, this approximation of the area under the curve, is going to be greater than the exact area under the curve of your given function from x is equal to 1 to x is equal to 5. Now part B, doing the exact same thing, except this time we are using right endpoints, meaning this Riemann sum is going to be a right Riemann sum. It's going to be a right-hand approximation. And since our function is decreasing on the given interval from 1 to 5, we know that this right-hand approximation is going to be an underestimate. And because this right here is the exact area under the curve, this area approximation over here would have to be less than the exact area under the curve. Now let's talk about continuity implying integrability. So this says if a function f is continuous on the closed interval from a to b, then f is integrable on the closed interval from a to b. That is, the integral from a to b of f of x dx exists. So all this is saying is that if you know your function is continuous on a given interval, there's no discontinuities within that given interval, then you know that you can take the definite integral of that function on that given interval. You can find the exact area under the curve of that given function on that given interval, just because the function's continuous.
What do you call an old ant? An antique! It's simple time!
Now example 1 says set up a definite integral that yields the area of the blue region. Do not evaluate the integral. So right here we have this triangular blue region, and we want to set up a definite integral that will give you the exact area of that blue region. Well, if you recall, a definite integral is going to go from the beginning of your interval to the end of your interval. So this area right here starts at x is equal to 1 and ends at x is equal to 3. So we're going to have the integral from 1 to 3 of your given function times dx. So what is this given function right here? Well, it's a line that has a y-intercept at -1 and has a slope of 1, meaning it's y is equal to x minus 1. So I'm going to take the integral from 1 to 3 of x minus 1 times dx, and that will give you the exact area under the curve of this given function on that given interval. Part B, doing the same thing. We want to set up a definite integral that will yield the exact area under the curve right here. Well, again, in our definite integral, we have our lower and upper limits of integration, which are the x values that correspond to the beginning of your interval and the end of your interval. So it's going to be the integral from x is equal to -3 to x is equal to 1. And we're taking the integral of this given function right here times dx. Well, the nice thing is they already give you the function. So we're just going to take the integral from -3 to 1 of your given function right here times dx, and that should give you this exact area under the curve right here.
Queen ants have wings, and they lose them when they start a new nest. This is crazy. You try.
Okay, doing the same thing, I want to set up an integral that will give us this exact area right here. So we know that in our definite integral, we have a lower and upper limit of integration, and those are just going to be the x values of your interval. So we're going to take the integral from 3 to 4 of your given function times dx. Now, on this interval, what is the equation of this function? Well, this is a horizontal line, and we know the equation of a horizontal line is y is equal to a number. So what does y equal in this case? Well, it's 2. So the equation of this line right here is y is equal to 2. So when I set up this integral, it's going to be the integral from 3 to 4 of 2 times dx, and I'm done. For part B, doing the same thing, I want to set up a definite integral that will give us this exact area. So, in our definite integral, we start with our lower and upper limits of integration. Those would just be the x values that constitute your interval right here. So, it's going to be the integral from x is equal to -5 to x is equal to 5. We have our lower and upper limits of integration. Now, the question is, what is the equation of our function right here that we're going to integrate? Well, we know that this is a semicircle, and the equation of a semicircle is y is equal to the square root of r squared minus x squared, where r is the radius of your semicircle. So what's the radius of our semicircle? Well, it's 5. So our equation of this semicircle would be y is equal to the square root of 5 squared minus x squared, or y is equal to the square root of 25 minus x squared. So if I want the exact area under the curve of this semicircle, it would be the integral from -5 to 5 of the square root of 25 minus x squared times dx. Now, example 2 says sketch the region corresponding to each definite integral, then evaluate each integral using a geometric formula. So here we have the integral from 1 to 3 of 4 dx. So this right here wants you to find the exact area under the curve, this function y is equal to 4, on the interval from 1 to 3. So the way we do this, the way we sketch this, is we're going to start with our function in here, y is equal to 4. So when we sketch y is equal to 4, that's just going to be a horizontal line at y is equal to 4. Now, we're going to shade the region between x is equal to 1 and x is equal to 3 under that given curve. So it's going to look something like this. We then see that we have created a rectangle. So to find the area using a geometric formula, we just have to use the area of a rectangle formula, where area is equal to base times height. So what is the base of this rectangle? That would be 1, 2. What is the height of this rectangle? That would be 1, 2, 3, 4. So 2 times 4 is going to equal 8 units squared. That's going to be the area of this rectangle. That's going to be what this definite integral is equal to. Part B, doing the same thing. First thing we do is sketch our function. Our function is in here, y is equal to x minus 1, meaning we have the equation of a line with a slope of 1 and a y-intercept at -1. So if we sketch that line and then shade under that line on the interval from x is equal to 1 to x is equal to 3, we get a triangular region that looks like this. Now, how do we find the area of a triangle? Well, we use the area of a triangle formula, where area is equal to 1/2 base times height. What's the base of this triangle? That would be 1, 2. What's the height of this triangle? That would be 1, 2, also. So what's 1/2 2 times 2? Well, 1/2 times 2 is 1, times 2 is 2. So the area of this triangle is 2 units squared, meaning if we were to evaluate this definite integral right here, it would be equal to 2.
What do you call an ant who lives alone? An independent. You try.
Okay, doing the same thing here. First thing we do is sketch our given function in here. Our given function is y is equal to x plus 2. We have the equation of a line with a slope of 1 and a y-intercept of 2. We are then going to shade the region under that line between x is equal to 1 and x is equal to 3, and we get something that looks like this. Now, we have to use a geometric formula in order to find this area. So what is this shape? Well, it's actually a trapezoid that was tilted backwards. Here, this is one of the bases. Here, this is one of the other bases. And the distance between the bases is your height. So that would be this distance right here. So to find the area of this trapezoid, we use the area of a trapezoid formula. Area is equal to 1/2 the sum of the bases times the height. Again, we said that this was one of the bases, 1, 2 units. This was one of the other bases, 1, 2, 3, 4, 5 units. And then your height is the distance between the bases, 1, 2, 3 units. If we were to simplify this, we end up getting an area of 10.5 square units, or units squared. That would be the area under the curve on this given interval. That would be what this definite integral is equal to. Over here, part B, doing the same thing. First thing we need to do is sketch our function. So our function in here is y is equal to the square root of 4 minus x squared. Oh, this should look vaguely familiar because it's in the form of a semicircle. Now, since we know it's a semicircle, the only question is, what is the radius? Well, remember, a semicircle is in the form y is equal to the square root of r squared minus x squared. That means in this case, 4 would be r squared, meaning that our r would be the square root of this, which is 2. So our radius of our given semicircle is 2. So we're drawing a semicircle from x is equal to -2 to x is equal to +2. And we're going to shade that region under the semicircle and above the x-axis. So it's going to look something like this. Now, in order to find this area, all we have to do is use a geometric formula. Well, what's the area of a circle formula? That's pi r squared. And because it's a semicircle, we just have to take half of that. So area of a semicircle is equal to 1/2 times pi r squared. Again, our radius here is 2, so we just plug that in here. We simplify, and we end up getting the exact area under the curve here is 2 pi units squared, or square units. That's what this definite integral up here is equal to.